Welcome to Part 8 of our Kornucopia ML Quick Start training. This video explores the second workshop, Cleaning Messy Tension Data. Please visit our website at boditech.com for additional details on downloading the accompanying PDF course notes and other training files.
All right, so the second example is going to be an example that's me cleaning up some messy tension data. So this is not accelerometer or anything like that. This should be data that would be typical that you would get from a uniaxial tension machine, where you might be pushing a measurement of a soft structure where the load cell is kind of on the low end of its capability. So you get a little bit of noise in the data, or you're testing a very challenging material like a non-woven sheet or some other material like that that's got a little bit more of a complicated material response. This example is going to take you through the following analysis steps. So we'll be importing multiple data files, one file per sample. So we'll show you some efficient ways to do that. And then for each of those samples, we'll be cleaning up the force displacement data, which will mean we'll be trimming off an initial distortion that occurs at the beginning of the test that's due to some initial slack that was in the data. And then all the measurements are tested through and beyond failure. So we'll be trimming the data at the end of each curve where it drops off. And then we'll be taking each one of those curves after we've trimmed them and smoothing them up so that we remove some of the noise that's in the data. And then we will do something called tweaking. That's a cornucopia concept to heal the beginning of the curves where we had trimmed off the original distortion. And then we'll be taking the curves and turning them into nominal stress strain curves, and then computing an average to get a single stress strain curve. And then we'll isolate the beginning portion of that curve and curve fit it to get an estimate of an initial modulus. So just like the other workshop, there is a version of this workshop solution. It's in this clean and messy tension data folder, and that folder itself is the cornucopia solution and the data. The data here is 5 files, one per each sample. And if I open up one of these samples, we could see it has some header text and then a little bit of header text that we might want to isolate, and then the actual tabular data itself. This also happens to be a comma separated file. So all of the 5 data sets are of a similar format. Actually, I'm going to open that back up. We'll leverage part of the top in a copy paste operation. And we also have a picture here of the test setup. So we're going to actually be importing that picture as well into our workbook. So I'm again going to create a solution from pretty much a blank sheet, but I will, to make things a little more efficient, I will copy a few things from the example I just did in this new approach. So in particular, I will start by just copying the top. We'll put this in the folder where I want the script to go, and I'll call this example 2. In this example, we're going to start off with a similar thing. We're going to have cleanup. Now, this time, we're not doing a shock and vibration kind of problem, so I'm going to pick a different thing. And since you might not be familiar, we will again do the question mark approach. And I'm going to pick a millimeter Newton and second preference. So whenever I do calculations, they'll be in millimeters, newtons, and seconds. And in this particular example, we don't really have any units variables that we'll likely be using, or at least not at the moment. We'll keep the advanced variable approach like before, and we'll turn off the warning when properties aren't inherited due to complicated math. We'll give our title something a little bit different. We'll keep the fig zoom the same. That's a reasonable size figure. And just to demonstrate the flexibility, we'll just change this variable here slightly, and we'll open up 10 slides, 10 tabs. So this starts off very similar to before. We're going to say, yeah, clear off. If I said clear only, then the figure window that's currently in existence would stay open. When I say yes, I'll wipe that out. So since this problem really has nothing to do with the other one, we'll wipe that out. And now we have our figure window. Just going to set it off to the side as we start to decide to populate the problem. So in this example, since we have a nice picture of the test, in our first tab, we'll put in a little overview, which is a good thing from documentation purposes, especially if you ever inherit somebody else's work. It's nice to have an overview. And we will leverage from the other workflow this as well, since I'm not really wanting to just type for the purposes of typing. So we're going to have a current tab. We change this variable from tab stuff main to tab stuff. It could be Fred, doesn't matter. Demonstrating the flexibility from that viewpoint. And it's not going to be raw acceleration plots. This is going to be an overview tab. So what do we want to put on the overview tab? I want to specify the picture that's in that data folder. So the data directory is, as I showed before, up to /data. On a Windows machine, the slash can be forward or backwards. It doesn't matter. On a Linux machine, it would have to be in this direction, I'm pretty sure. Now I'm going to specify the name of a picture file. And the picture file's name is this test setup PNG, so we'll just copy that. Now what I want to do is I want to display this picture into the tab. So there are native MATLAB commands that will do that. If you do that, you'll spend a bit of effort to do that, one. And two, if you ever change the size of the figure window and whatnot, you'll notice your picture won't change size very well. So if we use Kornucopia's kpic display function, it will do a bunch of extra stuff behind the scenes for you to make it easy to input. And if the figure size is changed, it will properly update the image and scale it in an appropriate way. So what we need to do is specify the name. So I'm going to use the full file function in MATLAB. And what I'm going to feed in is the data dir. So that's where the data is, and the pic name. PicF name for the file name of the picture. So that will give me a fully qualified file name. And if we open up this help, it wants to know where should I anchor the picture. We can specify a 4-coordinate location of normalized anchor location, or more conveniently and easily, we can specify things like north, center, southwest, and things like that. So we're going to specify that it's in the north, which would be the top center of the page. And we need to tell it what place this is going. So it'll be into the current tab. And if we specify it at the north, it will literally put it right up at the tippy top of the tab. So usually we like to nudge that down a little bit. So there's a command called nudge, or an advanced option called nudge. And we can nudge X and Y directions, which we don't want to do, so that's 0. And we'll nudge it downwards just a little bit. So this is a normalized coordinate. And it would also be nice to give a title to our image that we're going to put in here. So we'll specify a title text. And we'll specify this as test setup. And we'll have it show us the current tab. Again, I'm using a tab completion. Hit the tab key to get it to help me autocomplete some of these variables. So now when I run this, I now have a nice picture of the test set up. So this is the test that we're going to get some data from. Now, maybe we would like to put some description down here of some text of what it is we have in the test. So I'm going to copy from some text I previously wrote, some text that we would like to display on this. So this is some useful description that somebody might put about the test. Now I'm going to tell it that I want to display that text. I want to display it in the center towards the bottom. I got to give it a parent command so it knows where to put it. Otherwise, it'll put it in the last hot axes, which actually is a thing that the picture is held in, and then that wouldn't be helpful to us. So I want it to be in the current tab. And then I'm going to turn the box on. And I want to align it. Now, maybe I don't know about that command, so I could go and look here with help. Or since I have an ADV variable, I can do ADV, the function name, and oh, there's a line vertical. That's what I would like to do. I would like to line vertically at the top so that the top of the text box will start at a third of the way up from the bottom, basically. So I issue these commands. And I tell it to bring me back the picture. Here we now have some nice text set up describing the problem. So depending on the nature of your problem, you can specify as much text or as little or none if you want. But this is generally a good thing to do, especially if people are going to be inheriting your workflows. All right, so our next step is to read in some data. Now, we have 5 data files. So we could open up the MATLAB wizard and import one at a time, 1, 2, 3, 4, 5. And if we don't copy any code and make a for loop, every time you run the script, you got to do that. That's kind of painful. So we don't really want to do that. So instead we're going to do is we're going to have Kornucopia help us get quickly a list of the files in the folder of interest. And then just use a for loop and easily quickly loop and read in the data files. So we're going to make a list of file names. And Kornucopia has a thing called dir list. This is a little different than MATLAB's dir function. MATLAB's dir function will return to you a structured array of files and their sizes and dates and a whole bunch of other stuff. We're not really interested in all that complex stuff and dealing with a structured array. Instead, I just want a cell array of names to go easily reference. So that's what dir list will do. So we need to specify where dir list should look. And again, we'll put our directory back to where our script is. This is normally where you would have it. So I'm going to tell dir list to look using full file again at the data directory. But if I do that and do that only, and then say, give me all the files that are there, it's going to give me a list of files that include the picture. I don't want the picture. So the reason I'm doing this dir list thing is I wanted to search for star.txt. So what this is doing, this is combining the folder name with that, and it's going to search for, in this data folder, it's going to search for anything that's star.txt. And it will only be looking for files. It will not be looking for folders itself. And so now I have this nice list of file names. I can use that to easily loop and go get the files and read them in. So I want to read them in with kReadText. So I'm going to use the same trick as before of clicking on its brief help with F1 key, and then clicking the command to go get the template. And then I'll just paste this in here. And as before, so you need to, when you first learn this, read the information I'm deleting, but I'm telling you basically what's there. All right, so I've already dealt with data_dir from before, so I don't need that. The file name is going to be these two commands for file fname and file name. They're going to be referenced when we do a for loop, which is down here. So in the file, what do we have? Oops. So in that data file, I thought I'd open that up. We'll reopen it up, I guess. In the data file, you see we have a comma delimited file. Specimen dimensions with a capital D up here is what we need to be searching for to isolate this header section of the data. This will be part of the main header, but this is the header section of the data we want, and then the tabular data is here. So we'll make a few changes here. So right now, this is a case-sensitive search for this string, so we want to make that with a capital D because it happens to be specimen dimensions. When we find that, we want to step down one row. We find that we want to step there, and there's where we want to collect. So this setting at 1 is okay. For our column headers, time is good. I don't see time anywhere else, so that'll be unique to search for. If I saw time elsewhere, then I would put in maybe time, comma, space, load. That's unlikely to be found anywhere, and I would have put that for this argument. But since time is uniquely found, that's fine. When I find that, I don't want to further shift around in the file, and Kornucopia will figure out the column names and the units. And then there's no end string to end with on this. So now we're going to go and do a for loop. And when we do a loop, we're going to store the raw data in a cell array. Now, I see here there's 5 things, so I could put a 5 here. If I do that, when I go to make the for loop, I put a 5 in the for loop like this. Now I'm making Z my loop counter. If I put a 5 here and I put stuff in between there, this will work fine for this one example. If the next example has 4 data files and the next one has 7, this won't work because it'll give errors. So what I want is how many files. So I'm just going to create a variable, maybe n files. And MATLAB has 3 different kinds of ways to get how many things are in something in an array. We can do size. Size will tell you rows and columns. So knowing that this is a column array, so it's 1 column and multiple rows, I could issue a command like this. And that would say, give me the number of rows. If this was a 2, it'd be give me the number of columns. So I could do something like that, and that'll return 5. I alternatively could do something like this. Length. Length gives you how long a vector is, or if it's an array, the longest dimension of the array. So I generally avoid using length because if I, for some reason, instead of having this, I start having an array that has 2 dimensions, like rows and columns, then length will give you whatever is the longest dimension, which can be somewhat erratic depending on what you're doing. So I generally don't use length. Sometimes I will use size, but what I often prefer to use is numL, which is the number of elements. And so there's 5 elements here, it'll give you that. If this was a 5 by 2, it would say there's 10 elements. And it'll give you how many elements are in an array, which is usually a very generic and useful way to look at this. So now I have the number of elements, and so then I'm going to use the variable n file here, and n file here. And the reason I'm doing this is that I can then point at some other directory with 7 files and it'll just all work. I don't have to worry about anything. Now inside my for loop, I'm going to first determine the file name that I want to get. And the file name that I'm going to want to get is doing a full file on the data dir and stepping through this one at a time. So the curly brace steps into the cell array. That'll give me the file name. And then I'm appending the data directory. Then I'm going to read in the array. I'm going to use the variable temp here. The reason I'm doing that is sometimes I want to potentially do some other manipulation before I ultimately store it. This particular case, I'm not. So I'm going to just store it right into the raw. It's a cell array that I'm filling up. So that's not needed. And so now if I run this little section, okay, so that says end files, that says end file. So it's a little typo of the character. Try that again and I'm sure we'll be fine. Now I have a cell array of the data sets. And if I go look at like the third one, that'll indeed be the third samples data set. Now that I have all that, I want to make a plot. So I could quickly just make a plot like this. And if I attempt this, we're going to get a little error. And the reason we're getting an error is not because I'm feeding a cell array in, which is what I'm doing, because remember, it's a cell array of data sets. I will be getting an error because in an XY plot, you cannot plot with more than 2 types of compatible units. In this data, there's time, force, and displacement. We get an error when we feed in all the data because it tried to plot load versus time, and then it tried to add the laser data on the y-axis with the load. But the units of displacement of the laser were incompatible with that of the force units of the load. Just 1 second, the picture is up where the zoom window is. Okay, so that's not going to work. So then you say, oh, I know what I'll do. I will specify that I want the plot to be the laser displacement and the load, where the laser displacement would be the x-axis and the load would be the y-axis. You say, that's what I want to do that. So let's compute that. And MATLAB says, hey, I have an error here. And the error is not this one from before. So let's do home so we can clearly see what the error is. One more time. MATLAB says the index number array exceeded the array of elements 5. So what's going on here is raw is a cell array. We cannot reference the column names that are inside the elements of the cell array at the cell array level. We have to step into it. So that would be complicated. You'd have to make a for loop and do hold on and all that stuff. So instead of that, Kornucopia has a nice, elegant solution for that, which is we feed in the entire cell array, and then we specify the independent argument, which we want to be the laser, and the dependent argument, which we want to be the load. Now, the plot will work and all the data shows up, nicely labeled with a legend, the whole 9 yards. Now, if you don't have data that has names or each data set, the naming is inconsistent, you could have instead said, okay, I'm going to put in, so laser, which one's the laser? I'm not sure. Let me quickly take a look. Laser's the third column. So I could have put it in like this and leave the other one as load. I could have done that, or I could say the load is the second column, and I could do that. I can make a plot like that. So it's very flexible on how we do that. Now, instead of doing this in individual figures, we're going to leverage the fact that we have our figure window. So we have our original figure window, so it's not this. or these edits here, but we have our figure window here. So we want to put on tab number 2, the plot of the raw data. So let's do that. So we'll get rid of that. And we'll come up here and we'll copy our tab stuff that we're going to manipulate. And we'll put our ending display for the tab region. So this is the raw data. This would be our second tab. It's raw data we're going to plot. So what are we going to do? We're going to issue a plot command. And we're going to issue the plot of the raw data. So we could just put raw in here. I would generally recommend you do this trick of this, because then you can copy plot commands from other scripts quite readily. Specify the parent to be the current tab. And now we're going to specify the independent data. And the real word is independent call, but we can type short as we've talked about before. So that's the laser. Now, let's say I type laser with a lowercase l, not an uppercase. Column names are case sensitive. I'll show you a feature that Kornucopia has to help you with this a little bit. And for the dependent column, we'll reference the load. And then instead of using the ADV variable, I'll just demonstrate, since I do this a lot. We want the grid to be both major and minor, so that'll put the grid like that. We're missing one dot here. The continuation is always 3 dots. Now we could issue this plot. And you'll get this flexible match found. So Kornucopia is looking for the word laser lowercase, and it did not find that in this variable, but it did find the column name with uppercase. So it gives you some flexibility of dealing with this. In general, my suggestion is you try to fix your script to point at the proper name, but you can say, no, don't be strict, be flexible in the match, and do it only for this instant, do it for this particular session, or do it for all sessions. If you do it for all sessions, it'll put a setting in a Kornucopia file that will be on your computer that if you then want to go back to the other way, you'd have to change that and remove it. So I generally wouldn't recommend that. But if you really have a data set that the person was not very organized and they're very sloppy with this kind of thing, you might choose to turn on the flexible things for at least this Kornucopia session or whatnot. Here, I'm going to hit cancel, which will just end up throwing an error saying, hey, it didn't match. Couldn't find that. And I'll make it capital. And then you will see that this will work and we'll have a nice plot. So here's our original data, nicely plotted. Now, the lines here are a little skinny, so I might want to fatten them up a little bit. So I'll add a line width command. Something I could spell. And I'll just make the line width 1. By default, it's 0.5 width. So now it's a little bit thicker. You could set an array of line widths for different ones. You can control the color. You can do all kinds of stuff, all with Kornucopia functions of ADV options for the plotting command. All right, so now what we need to do is we need to clean this data up. So the data has some offset variation here at the beginning. It's also a bit messy at the very beginning. This is like a complete disaster kind of thing here at the beginning, but if we trim this off, the rest of it looks a little wobbly, but it's salvageable. The beginning is not part of the material measurement or anything like that. And that was the response of the laser squiggling back and forth and the crosshead in the noise floor before the sample tightened up and then became responsive. So we want to cut that away, and then we want to find the peaks of each curve and cut that away to get rid of these drop-offs. Now, one of the things you got to be careful of is you look at this, you want to do something, and you hit X. If you hit X, you kill the whole workbook, and then you got to recompute it. So you don't hit X on that. Otherwise, you'll be constantly recomputing your plots. Okay, so we're going to clean this up. We're going to trim off the front and at the peak. Once we have that, then we'll have data that we can filter, and we're going to use a Kornucopia smoothing function that really does IIR, low pass filtering, but it's set to be really easy to use, especially for this kind of data. And then we will heal the data that we trimmed at the beginning, heal that back, and we'll then line up everything so everything is aligned, and we'll have a healed, cleaned up data set. So it'll be just a few commands and a for loop to achieve that. So we will build that right now. So we're going to keep the variable cleaned to be the thing that's going to store the clean data sets. We're storing each data set cleaned in the cell array. And we want it to be however many data files we have in one column. So it's going to be our bucket that'll hold our clean data. And we will start with a for loop. Our Z will be our for loop counter. And as we step in, a nice approach, so raw here, right, is a cell array of our data sets. The whole idea of a for loop is we're going to step in and each data set at a time will process. So it's helpful to do things like this. Oops. So as we step in and are looping, we're grabbing the data set and assigning it to a variable. You don't have to do this, but if you don't do this, your equations and statements will become more and more complicated to read because there'll be lots of curly Z's and this and that in there. Usually when you for loop, temporarily assigning something out of the array into a variable and then referencing that makes your code easier to read, or your script easier to read. All right, so the first thing we want to do is we want to trim the data. Now, classically in MATLAB or other codes like Python, the way you would trim data is the data is in an array. So if I just start this off here and just look at the first data set, it's an array. And normally you trim an array based on indice locations. So I don't think anybody can tell me in the class here what the indice location is for each data set to trim it right around here. It's very hard to know that. That's not the way we're looking at the data. The way we're looking at the data is we're looking at a plot of load versus laser displacement. What I think we could all agree with is from a load perspective, this is 5 newtons. This dashed line here is 1 newton. If we were to trim this at 1 newton, we would definitely get rid of all this stuff. So that's a reasonable thing to do. Say I want to look at the load axis of the data and trim based on load, not based on indice. So in Kornucopia and in MATLAB, the way we're going to do that is we're going to use a function that will allow us to trim the data. It will return the indices that are meant for the trimming we're asking for, but the arguments we put in are based on things we're looking at in this graph, like load. So the command looks like this. The index list that we're going to generate is going to be derived from this function k_trim indices. And the trim indice function wants to know, give me a column vector to trim. and then what are the values that you want me to trim it at, and it gives you a chance of two values, a first value and a second value. So think of like a string or a rope. You have a pair of scissors and you're cutting it at two locations, and in between the two locations, that's what you're keeping. So in this particular case, the variable we're going to trim from a column perspective, so we're going to take the variable temp, which is currently echoed here, and we're going to reference the load column. So I could type it like this. That would be referencing the load column. Or if I want to be indice oriented, I could type something like this. That would be like a more MATLAB traditional way to write the reference. Again, I find this, unless I'm purposely looping somehow on columns or something, and that makes it sense, just picking that is often not as easy to read later as referencing the column name of the data. So I'm referencing that column, and now I want to trim at 1 Newton. So I can type here 1 Newton. And again, Kornucopia will take this string. It's an argument to a Kornucopia function, so it'll automatically pass it through k units and turn it into truly 1 Newton. Now, on the other end, I want to trim at the max of this data. So I just say max of the vector of the load vector. And that's it. If I evaluate that, IDX over here is a very large array of logicals. And if I just type a few of them, the very beginning of that array is all zeros. If I open that up here, it's all zeros, but eventually it becomes a bunch of ones. And then eventually at the very end, it'll go back to zeros. And what that is really telling you is all these data points weren't part of what's being kept, because I put a cut here, and then for each curve, I put a cut at its max. And so then it'd be a bunch of ones, which means keep all this data. And then the last few data points are zeros, which means don't keep those. So that gives us an indice, which then allows us to say our trim data is going to be the temp data of the index, all columns. And so if I just compute that, you can see that I have this array that's trimmed. It starts at a different place than the original temp did. Temp originally started at time of 0. That's clearly not time of 0 because it's gone and cut off the beginning of the data. And it's also cut off the end as we've requested. Now that I have that curve, I could make a quick plot here. I'll just demonstrate a quick plot of what is there. And I'll just do this. I'm just demonstrating on a single plot. So now that's a trimmed version of that curve for that one sample. And then we're going to smooth this up so it's not so noisy. That's not wildly noisy to begin with, but nonetheless, we could smooth that up if we want. So the Dsp smoothing I showed you before used the low pass Butterworth filter. Here we're going to use a function called ksmooth that has all that kind of stuff under the hood, but it's designed so that you can easily just put in a single normalized smoothing factor. So I'm going to put in a variable smooth fac, and I need to define that. I could either put the value in here or I'll just define it outside the loop. And I'm going to set the smooth factor to something like 0.9. So this is a number that goes from 0 to 1. It can't ever actually be 1, but as it approaches 1, the cutoff frequency is being set to a lower and lower value. The data is getting more and more smooth. As you go to numbers like 0.8, 0.7 and stuff, the cutoff factor is very high and there'll be almost essentially no smoothing. So I've smoothed the data, and for the moment, I'm going to claim that that's cleaned, and we're going to look at that. Then we're going to fix a couple things and generate ultimately the final result. So I'm going to claim that this is the cleaned version. It's not fully yet, but we will claim that for simple purposes of demonstrating this. And then I'm going to plot the data. So I'm going to initially just plot it in one fell swoop. And then we will change this. So I'm just copying the same kind of approach from before. Now this will be our clean data. And we'll generate this plot. If I compare the original raw data to the clean data, I've cleaned off the part at the beginning, but they're not lined up. I've got rid of some of the wiggles, but not all of them. And it would be nice if I have the clean and raw data on the same plot as opposed to having to flip back and forth. So let's address those couple of items. So the first thing I'll do is I'll address the items of the plot. So I'm going to do a subplot, and we'll make a subplot like this. So this time, I'm setting the subplot to something. The reason I'm doing this is so I can show the explicit reference of the plot to the parent. I don't really have to do this, but this is a good habit to do. But I was showing you before was a little bit lazy in terms of not putting this variable and relying on the fact the subplot occurred right before the plot. So that was the hot axis that the plot went into. Here, I'm making sure, no doubt, this plot is going into that subplot region. So the first thing we want to plot is not the cleaned, but it's going to be the raw data. And in this particular case, we're not going to use the two-plot approach. And then I'm going to put this as the clean data. And we want to put a title on each of these. So the title is something we're going to user specify, something I could spell, title. So it's a user version of the title, and this is going to be the raw data. And copying that, this would be the clean data. And this will go into the second spot. So if I run that, we now have the raw data and the clean data. So now what we need to do is we want to clean this up and get this to extrapolate back to zero load, and then align it all to zero displacement. So that means we have to do a little bit more than just smooth it. We want to tweak it back. So Kornucopia has a function called k_tweak, xy. If we open this function up, I'm going to open up the actual help page. It has a modestly lengthy description of what the function's all about. I'm going to demonstrate it here briefly. The argument list is modestly long. You feed in the data itself, and then you feed in some additional arguments that describe what you're going to be doing with the tweaking and what side of the signal you're doing this on and such. And this will be clear in a minute, but every one of those arguments is fully described here in the help page. There are several advanced options, and then there's some simple examples. And what these examples show is you can take a function like that, like data set this that was trimmed and is short, and you can tell it to grab a portion of the data and then curve fit it linearly or with a nonlinear polynomial and back extrapolate to either like the force is 0 or the displacement is 0. You have control over this. And you can take data sets like that and effectively heal them to make them be fixed or cured. So this is basically what we're going to do with this tweaking function. So we're going to set that equal to something, we'll call that the healed data. So we're going to tweak the smooth data. And we're going to use a linear extrapolation. And we'll tell it to take 0.1, basically 10% or 0.1 of the arc length of the data curve to use as the basis for the linear fit and then extrapolation from that. We're doing that from the starting end of the curve. And what we wanted to do is we wanted to look at the load axis of the smoothing data, and we wanted to extrapolate that back to 0 newtons. Because the one thing you would typically know in this test is where 0 load was. Now I'm going to add an advanced argument initially for this. And then advanced argument I'm going to use the ADV variable to get that for me. And what I want to control is what gets returned. And what I want to pick for return is I want it to show me all the details of this little calculation. If I evaluate this one thing, this happens to be the last file on the list, I'm going to get a little plot that's going to show me how this function works. So here is the data. And the master column is the load, so that's what I'm referencing. And the independent column by default is the first column of the data, which is not the laser displacement, but is time. And this is how it would extrapolate back. It would grab this portion of the curve, which is 10% of this arc length, and then extrapolates backwards linearly until it finds the load is 0, and it'll cut it at that point. And this would be a nonlinear extrapolation, which, since the data is fairly linear, is almost the same. So this is a really powerful function. I definitely encourage those who need this kind of thing to read the help, look at the examples that it's used in to fully understand its capabilities. Now I'm going to I'm going to disable that. So in MATLAB, if you put a % curly brace, then have some stuff, and then end with % curly brace that's closed, that will basically turn all of that section into a comment. And then I will do the real thing without showing the plot as it loops around to heal the data. And then our clean data is going to be the healed version. Now, if we just do this, we will achieve the following result, which gets us close to a healed set. So now they all go to 0 load, but they're all not aligned this way. So we want to line them up so they all start at 0 laser displacement. So we just have to add just a couple more calculations here. So for each curve, there's an offset of the laser didn't start at 0. So I'm going to compute that and store that for each curve, displacement offset equals the healed data. The first value, so what I'm basically isolating is this first data of the laser column. So that's the displacement offset. And then I want to subtract that from the healed data. I'm going to keep that because I'm going to use that to more accurately estimate the strain by adjusting the gauge length because of these offsets. So I'm taking the healed data and then subtracting all columns. That's zeroing the data. And then I'm going to store, I didn't specify healed correctly here, little typo. And lastly, I'm going to store the yield data, this offset, in the properties, the user data of the properties, because I can then use it later in a calculation that we'll need. The variable I'm storing here is like a structure. This name doesn't have to be the same as this. It's just useful to do that. So what I'm storing is this offset for each data set as I loop around. And so now when I look at the clean data, it will meet my desire that it'll be all cleaned up, lined up, all nicely at 0, so that I can then take an appropriate average of this, which is what we're going to do in just a moment. So now what we want to do is we want to go compute, instead of load displacement, we want to compute a stress strain. So we'll make a new section. For simplicity on this problem, we're just going to compute nominal stress and strain. You could be a little bit more elaborate and compute a true stress strain curve by making some plasticity assumption calculations, but for this simple demonstration, we're just going to compute a nominal stress strain. So the nominal stress strain, again, is going to be for each data set, so we'll store that in a cell array. And we'll again loop over the data sets. And now what we're going to do is we're going to isolate and get the cleaned data for each data set. And once we do that, we want to get some information out of the clean data set. So what's in that clean data set? So it's a cell array. Let's just step into one of them. We have our data, and we have, from the original reading, we have header information. In the data set header, we have the geometry information that we need: gauge length, thickness, and width to turn force displacement into stress strain. So we're going to use that to do the calculation. So we're going to isolate that. So we'll call that geometry. And we're going to use the unpacked header function to nicely turn that into computable stuff. So here, instead of cleaned, we're going to reference that as temp because we're looping on that. And we have colon as our delimiter. So that'll get us our temp data. And now we need to adjust the gauge length that we thought originally was there based on the slack, which is stored in this offset. So let's just step in here and demonstrate what happens. Made a mistake. Z is 1. And this should be looping. Actually, this shouldn't be anything. That should just be temp. That was my mistake. All right, so now we have this geometry information. And now we want to compute an adjusted gauge length by taking the gauge length here and adding to it this offset, because since there was slack, the gauge length is actually bigger than we thought. So we could store that in a separate variable, or we can actually add it to this by specifying some new name, like adjusted gauge length. And we're doing this with curly braces over here, not smooth. And the curly braces are telling us that when we compute whatever, we're going to stuff it into a column name that's already named this. So what are we going to do? We're going to grab the gauge length. And we're going to add to it the thing that we stored up here. So when we do that, we don't need 2 dots, so I need 1. So this is getting, oops, that's getting the offset that we had. This is the gauge length that the specimen had originally. And it doesn't matter that one's in millimeters, one in inches. Kornucopia handles all that. And then this will compute the adjusted gauge length. So now we have the adjusted gauge length here. Once we know that, the next thing we want to know is the area, because we're going to need the area to turn force into stress. So the area is the thickness, which is right there, times the width. That'll be the area. And once we have that, we can now compute the nominal stress value for the temporary, for this component looping in the data set. So we'll say nom stress temp is, and we're going to want to have, this is for stress and strain, so we want to compute the strain, and then we're going to want to compute the stress. So the strain would be, we would take from the temp variable the laser displacement, and we would divide that by the adjusted gauge length. And we need this to be smooth parentheses on the right side, because we're not trying to step into anything, we're just trying to get the value. So that'd be the adjusted gauge length. So that will compute strain, and the strain is dimensionless. No column names are created, and we will rename the column names in a second. And then we want to collect the stress, which would be the load divided by the area. Now we're concatenating these two things together. So when we compute this all together and concatenate it, oops, we made a mistake. Oh, I didn't compute the area here. Here we go. So now we have strain dimensionless, stress in PSI or megapascals. So it'd be nice to have some column names to that. So we'll add column names. You don't have to add column names. If you don't add column names, then when you make a plot, the plot will have no labels, except for just units. And then you'll be making column names there. So my viewpoint is better to make column names as I'm computing stuff to keep stuff well documented and easy to follow. But those are choices you can each individually make. Now we're going to add the description. And we're just going to take the same description that was in the original temp variable. So now when we do this calculation, that's well described, strain and stress. Now, some people like strain shown with no dimensions like this. I generally, for most problems, like to show the units in like percent or microstrain, or maybe it's not, but often I like to do it that way. So I'm going to convert from the nominal strain column. I want to convert that strain to the unit of percent. And now that I have that, for that one data set, I'm going to stuff that into my SS variable. And now I've computed for all of these. I've computed nominal stress strain curves, and I can look at any one I want. And it's well labeled and computed. And I've turned the force displacement data into nominal stress strain data, which I can now go plot. And so I will just steal the plot command from up here. And this will become tab number 4. So this is no longer laser and load, and since there's only 2 columns, I don't even need to specify that, so we'll get rid of that. And we'll plot that. So now I've gone from a description of the test, raw data, cleaned it up. Now I have a nominal stress strain curve. Now it's still a little wiggly, so maybe I go back up here and say, oh, I want to make that a little more smooth, so I'll increase the smoothing factor. I recompute that. I'm just going to show the plot. Now it's smoother. Now I show my final thing. Now, had I done this in some manual approach with a lot of clicky-picky stuff, I would be doing that time and time again. So spend a little effort up front on a script, but then it's really easy to keep reusing it. Now what we'd like to do is we want to get an average curve to represent this data. And once we get an average curve, we'll then take from the average curve the beginning part to get an initial estimate of the slope or the modulus of the data. So we just have a couple more steps left. So for computing the average, I'm going to compute the average 2 ways. I'm going to first compute it quite simply, and then I'll use a little bit more of an elaborate approach. So the first average, Kornucopia has a function average xy. Now, let's just think about this for a minute. Let's pull that plot back up. Think about trying to compute the average of these curves. So you might think you would compute an average by going along at common values of strain and averaging. There's nothing that says that these data sets have common values of strain to do that with. The curves end at different locations. They start all at the same, 0, 0, but they end at different locations. And they generally do not have, everybody has a strain value at 10% or anything like that. So to average that all by yourself with just normal math will take quite a bit of effort. Kornucopia's average xy function will handle all those issues, do all the interpolation and whatnot needed to map the data so that you can average the data quickly and easily. So the data we want to average is the nominal stress strain data. This function similarly allows you to give x and y separately or give it together, which is what we're doing. Skip the second argument. And then we have an averaging method and then advanced options. So there's 2 forms of averaging method that Kornucopia supports. So one form is called the X method, which means it goes along at some increment in X and averages, where it does all the interpolation required on each curve to be able to do that. The other approach it does is it takes the curves and it computes an arc length as an independent parameter, and then it averages the data along common values in the arc length. Depending on the nature of your data, depending on the sophistication, what you're trying to do, there's a host of flexibility and options in this function. And there's an example in Kornucopia that goes over this in great detail. Averaging curves, that along with the help, which has a lot of stuff about it as well. But this example averaging curve shows you all kinds of features of this function that are really very powerful. Okay, so we're going to use this X method, and our first version is just going to be a simple average. And we're going to go make a plot. Now, I want to plot the average in addition to the different data curves. So I could add them all together on one plot, no problem. And then I would have 6 things in the legend, and maybe my original data wasn't 5 curves, maybe it was 20 curves, and then I'd have 21 things in the legend. It quickly kind of gets out of hand. So we really don't care to know any individual curve. We just want to see all the curves like as in one color as one thing, the data, and then the average as the second thing on the plot in some other curve. So Kornucopia has a nice function that will take data curves like that and stack them into a single curve with nands in between, so that MATLAB will easily process this. So I'm going to store all the nominal stress data with this function called stack for plot. and I just feed in the cell array of data. And if I do nothing else, Kornucopia will take those and stack those as one nice plot. So it looks like one thing, but if I scroll down, there's now many more rows. There'll be a nan in between them. I can actually demonstrate that. So if we look at this in the variable viewer, if I scroll down a little bit, we will eventually see nans. And that will be stuck between each data set. The reason that's done that way is that allows us to feed this to the plotter, and the plotter will make an appropriate set of plots, but view it as only one curve. So let's start making our plot. So we're going to make one big plot like we did before. So we'll just leverage this. This will become tab number 5. And this will be our average. So the first thing we're going to do is now we're going to make a cell array of things to plot. So this itself took a cell array of things and flattened it down to one thing with nans in between. So this is not a cell array itself. This is just data. And we'll plot the average. And we'll feed that to the plotter. And let's see what we get. So this is now the average SS, which I change that. We'll fix that in a second. So on this plot, the labeling is not distinctive because we didn't spend any extra effort to change the description of this particular variable. So we could do that, or instead we can manually define the label, which I'm going to do here to show that. And we'll manually do that right now. So we're going to change the legend text to be some manual definition of what we want to have show up on the legend text. And just for brevity, so we're not sitting here watching me do this all day long typing, I'm going to copy from the answers that I have the text that I want to put in here. So the first curve is going to be all the nominal curves, and the next curve is the average using default ADV options. We have no ADV specifications here. So now we want to tell MATLAB to use that. So we use the legend text argument, and we're not pointing at a particular object, so we're using a user option, and we're specifying this variable. So now that will show that nicely on the plot. There's the two sets of curves. Now the red curve doesn't stand out so well, so we'll maybe make the red curve a little fatter. So we'll turn this into an array, and we'll give the red curve twice as thick as the other data. Now we got a nice showing of our average here. Now the average goes up to where all the data is common. Beyond this point, we then start having less and less curves. And by the time you get over to here, there's only one curve. So from a purist viewpoint, this is as far as you really can average. But we're engineers, we're not purists. So we might like to be able to average farther out. So Kornucopia gives you methodologies to extend the average using influences of this data, but in a fairly smart, reasonable way. And so the help function and the example I just pointed out talks all about that. I'm just going to demonstrate using it so you can see what you can get with that kind of thing. But to really learn about its power, you need to spend a little time reading the help and its implementation. So again, speeding up a little bit for brevity, I'm going to copy the call for that. So I'm going to give this another name. The beginning is the same as before, but now I'm going to use these advanced options. And what I'm doing is I'm telling the thing to extend to the average last value of the data. So I'm telling it to take this average and compute it out to the average of the end values. wherever that kind of ends up, extend the average to that distance. And then use a second order polynomial method for the extension and have it influenced by this factor using the extension region of data to do this. That's what these parameters are doing for us. And the beauty of this is the following. And now I'll put in the elaborate description. So now I have the original average, the more fancy average. I still have it stacked. I'm using the same plot, but now I'm putting 3 data sets together. And we'll keep them the same for the moment, and then we'll do something with the plot in a second. So now the green one is the more fancy one, and the average went all the way to here, which looks very plausible. You can't tell the red curve because it's right under the green curve. So there are a couple ways we could tell that. One trick would be to make the red curve really fat. So if I make the red curve really fat, then you can kind of see the red curve under the green curve. I could do that. Another way to do it is to add some symbols. Now, there's quite a few points, so when I put marker symbols on, I don't want the marker symbols to be on every point. So I'm going to add some marker symbols. And I'm going to add that I don't want any marker symbol, which means blank, for the first curve, which happens to be the nominal data itself, the raw data, or the cleaned up version of the raw data. And then I would like hollow circles for the next curve and X's for the third curve. And I want to set the marker occurrence. I can either set it by a total, or I can set it by like every 5th or 6th data point. So I'm going to do a total. And these are all advanced options that are explained in the function's help. I'm going to say I want a total of 8 markers shown for each data curve. And the last thing I'm going to do, and I'm going to demonstrate this with the ADV selection, I'm going to go here to the markers, and there's a variety of marker things, and I'm going to force the markers at endpoints to be on, so that I'll get a final marker at the end of the shorter red data, or I mean the shorter default solution. And so when I make this plot, you'll see now I have a very informative plot. So the markers are not at every point, they're just indicating the curve, but you see the red ones stop here, and that's where that average ends, and the green ones go all the way to here. So as I stated earlier in the training, there are tutorials. And this tutorial here is a pretty significant tutorial. It goes through all kinds of plotting options and features like I'm demonstrating. I'm demonstrating just a small amount of the capability that's in the software. Okay, so we have our nice plot. Everything's looking pretty good. So the last thing we want to do is we want to isolate the beginning section of the average curve to then compute a current modulus. So we have our average curve, and we'll do this with the average B curve. So here's our average B curve, which from our plot, we could have equally have done this with an average A curve, but we'll just use the average B curve. So we want to isolate this between the beginning of the curve to, let's say, 4 megapascals. Isolate that part of the curve, and then do a linear curve fit to that. And then use that linear curve fit to then judge the slope or the modulus. So we're going to do our index trim like we did before. So we're going to do k_trim indices. And what are we trimming this time? We're trimming that average B, the nominal stress axis of that. We want that to go from the beginning, which is, we just skip that. And we want to trim it to 4 megapascals, I think was the units. Let's look on our plot. Pretty sure 4 megapascals. Yeah, 4 megapascals. Units here are megapascals. So we'll trim that to 4 megapascals. And then we'll just say some variable temp is the variable average B. For that, all columns. And we've now trimmed that data. And we could equally make a quick plot of that. See that indeed we now just have a kind of linear section of the curve going up to 4 megapascals. All right, so now we have our curve at 4 megapascals that we've trimmed it to. And we want to do a curve fit to that. So Kornucopia has a function called kFitFunc. And what it does is it does all kinds of different curve fits, including the units and everything. So it does a proper, accurate job of curve fitting. It's very flexible and very capable. So we're going to make a fitting function based on that. And we're going to feed in our temporary data, which is the trimmed version of this. So this is the linear region or anomaly linear region. We're doing it in the XY format. So we're going to skip the second argument because we would be putting in the XY data, skipping the second argument and putting in a fit basis. We can put in a variety of fit bases. We can even put in equations. It can be quite complicated. We're going to use a very simple form, which is we're going to do a polynomial fit. But the polynomial fit we're going to use is going to be a constrained polynomial. And the constrained polynomial will force the polynomial to go through 0, 0, which is what should occur in a modulus plot. And we're going to do that as a linear polynomial fit. And we're going to have the result of that show up in our thing in the current tab, which is going to be tab number 6. Which will be our modulus. Oops. So we have our parent, it's going to be the current tab. And we're going to compute that, look at it, and then we're going to do one little fix or one little addition to it. So here's our modulus assessment. There's the actual data. That was from the data, and there's our curve fit straight through it, and we're claiming that slope is the modulus. Now, the default naming convention for constrained polynomials have coefficients C0, C1, C2, etc. So we're going to just isolate that, and we're going to do that. I'm going to copy a couple things from the pre-made solution. So we're going to go from FitFunc. It has some things, and we're going to go get the fit constants. And if I look at the fit constants, it'll echo whatever they are. So if I did a higher order fit, there would be additional constants, but we only need a linear fit for this. And I want that coefficient. I'm going to call that E0. So I'm going to then make this text and turn that value into a string so I can add it to the text and display it on the figure, increasing the font size a little bit, and end up ultimately with this final nice result where I've stated what the modulus is. All right, so then we are near the end of this solution. So normally one would probably go to the beginning of the script and get rid of the things and make it go from 1 to 6. I'll actually quickly demonstrate that. So you'd probably go here and say, I don't really need 10 pieces of paper, I need 6. And then maybe we'll just quickly redo it. And very quickly we'll punch through each section. So it's going to add our picture with our comment. Put in our raw data. Cleaned it up. Computed an average. No, that's the nominal stress strain. We computed the nominal stress strain. Now we compute the average. And then the last piece here, we're doing our modulus assessment. And we have our thing done. Now, something I didn't show before. So before I go save the figure, I can attach things. This will explain what you have. You can get a list of what you have attached. You can remove the attachments, things like that. Here, we're going to store something to the figure file. I'm going to start browsing from where my working directory is, which is, stop that. Again, I have the working directory set back to the data, which is not what I meant to do. I want the working directory to be where my script is. So going back to the figure, I can go here and I can say I want to attach. Starting from my working directory, I can browse and say, hey, I want to attach my script, whatever it was. I can attach that to the file. And that says, do I want to attach anything else? I could say yes, and I could go attach a PowerPoint, a spreadsheet, all kinds of stuff. And what I'm doing is I'm attaching it to this one figure file. Here I'm going to say no for any more attachments. So now when I go and save this, that attachment will be saved as part of this file. Which means I could then give that to a colleague. And here, so I don't overwrite the other one, I'll add a 2 to this. Well, I could then give that to my colleague, and they could open it up and get the script back out, get the PowerPoint back out, get the spreadsheet, whatever I put in there, video, any of that can all be attached. And you can go see what's attached. I can say, give me a list of what's there. And then I can actually select that and pull it out if I wanted to. Here, I'm not going to do that, but I could pull it back out and start to use it. I've just saved the figure, and then I would generate the PDF like I demonstrated before, and then I would have a nice PDF of the results of this example. So I guess to be complete, we'll just quickly do that. And so now again, we'll walk through this thing. The PDF that I am showing, this only will work on a Windows machine. That requires a Windows component to do that. If you're on a Linux machine, you would use the options to create an HTML output instead. Then you have this nice PDF document, put it to 100% to be a little clearer, that you can share with anybody. So workflows that I typically do when I'm doing measurement work, I might measure 20 or 30 data sets. And these kind of things will have multiple layers of tabs, one for each data set, and a tremendous amount of information in there. And then I dump out this nicely documented PDF and have given the person an effective report in a few minutes. That's a really efficient way to store your data. We've probably, fortunately for you guys, have ended a little soon. So I'm just going to point out just a couple things quickly. So in this ball lens impact, this talks about and demonstrates reading data from a file that was from a solution simulation and from a test. The data is still in an ASCII format so that everybody can try this. If you were an Abacus user, the original data would have come from an ODB, and you would use some of the Abacus ODB importing that I showed earlier yesterday to have run in your data. And this shows using the K_regularize to regularize the FEA data and a few other things. This gives you a description of the kind of things you would do to process this example. And then the Moon penetrator is also a comparison between an experiment and FEA data. And there again, you'll have to do some manipulation of the FEA data to regularize it and such. And Beyond that, there's a lot of examples in the Kornucopia code that can help you. And if you are struggling or have problems, don't hesitate to reach out to us. Send us an email. Our contact information is on the web, on our website, or you can send an email directly to me, and we will try to help you out. Outside of that, that is going to be the official end of the class.
Thank you for attending, and have a great day.